All right, so this is about nonlinear inequalities, part 6, nonlinear inequalities. So you'll remember that we solved polynomial and rational equations in this chapter. Now we're going to solve polynomial and rational inequalities. So some definitions. First of all, a polynomial inequality would be a formulation like this, where you have a polynomial, some inequality symbol, and then some expression. So a polynomial related to an expression with an inequality symbol. And this could be any of the inequality symbols. There are 5: greater than, less than, greater than or equal to, less than or equal to, and also not equal to. So the sign chart, so this will be a chart where we have a list of zeros, and then we'll have f of x's behavior. So in other words, is it above the x-axis or below the x-axis? If it's above the x-axis, we'll put a plus sign. If it's below, we'll put a minus sign. And that behavior can only change in a continuous function after a 0. So it's a way for us to understand the bounds of f of x's positive and negative behavior. And if this doesn't really click all the way, that's okay. We're going to do a lot of examples with this. Every example today will include this technique. A rational inequality, just like a polynomial inequality, will have a rational expression. So some polynomial p of x divided by some polynomial q of x, and we're relating that to some expression with some inequality symbol. It doesn't matter which one. So a rational expression related to some other expression with an inequality symbol. And the other expression can be anything. As long as it has at least one rational expression, it's a rational inequality. Any questions about any of this stuff? All right, let's apply it. First off, task number 1 will be to relate your polynomial to 0. So I need to get 0 on one side of this equation. The way I'm going to do that in this case is subtract 1 from each side. So you need to get one side equal to 0. Now I need to find the zeros of the polynomial. So that's going to be discovered by setting it equal to 0 and solving for x. In this case, the most efficient way to do that is going to be by factoring, because that one just cries out to be factored and then solved with the 0 product property, which gives us x equals 5 and x equals 3. So if I create my sign chart now, I'm going to list the zeros in ascending order on the sign chart. And now I'm going to need to know the behavior of f of x, where f of x is that polynomial. And that's going to determine how we classify these sections as positive or negative behavior. So if the polynomial's function is above the x-axis before 3, then we'll put a plus. If it's below the x-axis before 3, we'll put a minus. And the quickest way to do that is with the calculator here. So if I pull up and use the second formulation, not the first. If you plug this in, it'll be wrong. So once you relate it to 0, that's the polynomial you're going to use for all the subsequent steps. So before 3, it's positive. Between 3 and 5, negative. And then after 5, it's positive. Above the x-axis, below, above. So above is a positive, below is a negative, and then above again is another positive. So we're looking for where this is less than or equal to 0. Do you see how that would only be true here? That's the only place where it's less than or equal to 0. So our answer is going to be x is an element of 3 to 5, and will include the bounds. So when it's a polynomial inequality, if it's or equal to, I include the bounds. It's a little different with rational inequalities because we have to make sure to exclude the possibility of division by 0. But if for polynomials, that's not a concern. If it's or equal to, we include the bounds. It's not, if it's just greater than or less than, you exclude the bounds. Any questions about that example? Thoughts or comments? Cool. So let's talk about one here. So see if you can do the same thing. Get this related to 0. Find the zeros, create a sign chart, figure out where the inequality is true. If you have trouble getting started, let me know and I'll come and help you. So you switch the signs around, but you got the right values. So this one should be correct. Yeah. So those will be your zeros for your sign chart. Sir? Very good. Yeah. Believe in yourself, brother. And then each of those factors will be set equal to 0. So those are your values on your sign chart. Good. And now you're going to use that to determine the pluses and minuses. Do like that. So grams of list. Something just right there. So it would just be. Exactly right. Very good, buddy. Spend just another 30 seconds or so on this. All right, so tell me the expression you got for this second step, Elizabeth.
X squared minus 9x minus 36.
Very good. Tell me how you factored that, Katie.
X minus 12 times x plus 3.
Excellent. And then, Isaac, what would the zeros be?
Negative 3 and 12.
Excellent. So they would go here. And then, Carson, tell me the signs for the function here?
Positive before -3, and then negative, and then positive.
Very good. Now, don't fall in love with the notion of these changing every time, because depending on the way that zero behaves, that doesn't have to be true. So don't just look at this one and assume it'll alternate. In this case, it does, of course, and in most cases it will, but not in every case. Just a caution there. And then our answer is what, Ashton?
-3, 12.
Remember, the boundaries are not included this time because we're not or equal to. Good job, guys. Excellent work. All right. I don't like all this mess, so let me move this to a new page here. So our first task is going to be to relate this to 0. I'm going to do that by subtracting 3x squared and adding 24, which gives us this expression. Now, to find these zeros, we could do the rational zero theorem, find a list, test them with synthetic substitution. If you just had, no reason to do it more efficiently, that would be okay. But the calculator is always going to be more efficient when it's possible. Now, do beware, some of these are going to have non-integer solutions. In other words, fractions. So you're going to have to use some calculator tricks to find those if that's the case. But the integer solutions will be easy enough to find. So plugging this in the calculator. Then I hit graph and I see -4, +1, and 6 looks like. Let's check the table. Start at -4. Yep. -4, 1, and 6. You see how that worked because they were all on integers? If it had been a fractional value, I wouldn't have found it in this table, and I would have had to have used some other tricks. But -4, 1, and 6. Are solutions to that polynomial equal to 0. So those are the zeros we're going to put on our sign chart. And we'll use the graph to determine. So see how steep this is? It's kind of hard to tell which way is doing what. But it's going to be negative to the left, positive to the right of the first zero. And then after 1, it's negative again. And then after 6, it's positive again. Again, don't fall in love with that alternating scheme. That won't always be true. So where is this greater than? Here and here. So the solution is going to be like so. And once again, we're not or equal to, so we don't include any bounds. Stop me if you have a question. Something's unclear to you, perhaps. Okay, I will assume then we're ready to move on. So sometimes we're going to get unusual solution sets with these. Unusual solution sets can manifest in this way. So this is a graph of x squared plus 2x plus 3. And where is that less than 0? In other words, where's the graph below the x-axis? None. It has no zeros. And it's always positive. So where's this less than 0? Nowhere. That has no solution. So no solution is possible. Unusual, but possible with regards to these problems. Okay, same expression. And And this time we're asked where it is greater than or equal to 0. So there's my little sketch of the graph. Remember, our sign chart was just always positive everywhere. So where is it greater than or equal to 0? All real numbers. In other words, everywhere, all the time. Doesn't matter what x you pick. As long as it's a real value, it's going to be a positive result. Okay, new one now. Here's the graph for it. Notice it has one intercept at x equals -6. Where is this greater than 0? It's everywhere except for the 0. So everywhere else, in other words, it'll be like this. So the way we write that is from -infinity to -6, union -6 to infinity, or if you like, x such that x is not equal to -6. Those are equivalent solutions. Second one's a little more efficient. I have no preference. Okay, once again, dealing with the same one. Where is this less than or equal to 0? Well, that's going to be only at the 0 itself. So x equals -6. So unusual, but possible to get a single value as the solution to your inequality. It's almost always a set, but not in this case. Questions about anything so far? All right, all right. So, Isaac, tell me where this would be greater than 0.
Everywhere.
It has a 0 here.
Oh, it's everywhere but -3.
So, now let's talk about a rational inequality. So these are significantly more complicated than just polynomial inequalities because we have to be conscious of a few things. First of all, we could never include anything that creates division by 0 in this original formulation. So I'm going to go ahead and make myself a note that x could never equal -2. Just put that in my back pocket and remember it. That throughout this problem, we're going to have to be conscious of that not being available because it's an asymptote here. So our step 1 is going to be get one side equal to 0. We've already got that, so we'll go to step 2, which is going to be combine terms. So I want to make this into one single rational expression. So I'm going to do that like so. Remember that to combine fractions through addition or subtraction, you need a common denominator. And the way I'm going to create that common denominator is to multiply 3 over 1 times x plus 2 divided by x plus 2. So that's going to give me a new value that'll have the same value of 3, but it'll have a common denominator so I can combine those like terms, like factor terms. So 3x plus 4 over x plus 2 minus 3x plus 6 over x plus 2. Now we have a common denominator. We can combine these, 3x plus 4 minus 3x plus 6 over x plus 2. Be careful with that minus sign, it's going to be really easy to make a sign error there. So let's continue on. So distributing that minus sign, I get this. And then I get canceling 3x and minus 3x. 4 minus 6 is negative 2 over x plus 2. And that's going to be our step 2 complete. We now have a single term, where before we had 2. So these are equivalent expressions, but in this case we've got a single rational term. So I'm going to create a sign chart, and I'm going to populate it with zeros of both the top and the bottom. So the numerator polynomial and the denominator polynomial, I need to populate this with the list of x's. So zeros from the num and the denom. In this case, only the denominator has a 0, and it's at negative 2. And if we look at this function's behavior, it's a little wild, but we can tell what's going on, I think. So positive, negative. And so if I find where this is greater than 0, it's going to be this region. And normally the inequality itself would call for me to include that negative 2. But you remember the note I made for myself? X could never equal negative 2. So that cannot be part of our solution. Even though the inequality itself would indicate that you should include the bound, it can't be included because it's a 0 of the denominator. So never include values that create division by 0. So our solution is going to be x is an element of negative infinity to negative 6. And we can't include negative 6 because it's outside the domain of the original rational expression. All right, any questions about that one? There is an often missed test question where one of the multiple choice answers is to include a boundary that should be excluded because of this reason rather. And often missed again.
What is it? Negative 6.
Oh, meant to write negative 2. My bad. Thanks, buddy. Misread my own handwriting, I guess, or maybe I looked at that. Okay. So let's do one more of those because those are pretty tricky. I'll make a note to myself, x could never equal positive 3. We're already a single term here, but we do need to get it equal to 0, and then we'll have to combine like terms. So x plus 5 over 2x minus 6 minus 1 is greater than or equal to 0. X plus 5 over 2x minus 6 minus, and I'm going to multiply 1 over 1 times that denominator divided by itself. Continuing on here, get x plus 5 over 2x minus 6 minus 2x minus 6 over 2x minus 6. We'll come over here. So that's x plus 5 minus 2x minus 6 over 2x minus 6 greater than or equal to 0. Hit that vape again. So I hate to have his bait bill. There we go. So distribute this minus sign once again is going to be real easy to make a sign error on this part. Now we'll combine like terms to get -6 plus 11 over 2x minus 6. We're ready to populate this with zeros. So the zeros at the top are going to be positive 11. Yeah. So that's one of our two zeros. And the zero of the bottom is going to be x equals 3. So we populate our sign chart with, that thing's just determined to be in the way. Populate our sign chart with the zeros of both the top and the bottom, and then we'll analyze the function's behavior. We need to put in this expression, not the original expression, because we had to modify that. So it'll mess you up if you put it in the original form. All right. So we see negative until, let me see, what did I put that in? 2x minus 6. Oh, that wasn't right. All right, there we go. Negative until 3, and then positive until 11, and then negative again. So negative, positive, negative. So where is this greater than or equal to 0? Right here. But we have to be careful. Normally you would include both of those. But remember, x can never equal 3. It's outside of the domain. So that's where it's greater than or equal to 0. From here to 11, including 11. Questions about that one? These get kind of messy. And you'll be constantly going back like, ooh, wait a minute, messed that up. So don't be afraid to go back and review your work and reconsider. It's very difficult to get these right in one go. All right. So that is what I wanted to show you guys today. Let me pull up the assignment here. Hey, Leslie. Chapter 2, part 5. Should be chapter 2, part 6. There it is. So page 145, 2 through 20 even, and then also 29. And you guys will have plenty of time to work on that. Oh.